All right, so rational expression. Today we are going to determine the domain of a rational expression and rationalize the numerator or denominator of an expression. So that's going to be a little bit different. We're going to talk about the domain. So some of that's going to be review from previous courses. And then rationalizing is also a skill we know, but we have not rationalized the numerator yet. Okay, so sometimes we're going to rationalize the numerator, other times it will be the denominator. So in general, an algebraic expression may not be defined for all values of the variable. So that means your domain is not all real numbers. Okay, so the not being defined, that would be when the domain is not all real numbers. Okay, and we know that the domain of an algebraic expression is the set of real numbers. So we can use the symbol, that's the real number symbol. Okay, that the variable is permitted to have. Okay, so we're going to fill out the table together. Do you guys remember any cases from last year where the domain could not be all real numbers? So it says it can't be defined. Where are situations where we have something that's undefined? Yeah, remember?
If x equals 0.
Yes, you can't have 0 in the denominator of a fraction. If you try to divide by 0, that's when something is undefined. That's the first one we're going to put in our table. So if you have 1 over x, okay, your domain, set builder notation, would be x such that x cannot be equal to 0. Okay, so anytime you have a fraction, we know that whatever the denominator is, because the denominator is not always going to be x. So for fractions, we know the denominator cannot be equal to 0. Sometimes you'll have to solve that. Okay, there's one more that we really pushed last year. There's a couple more situations that we talked about. So besides having 0 in the denominator, yeah?
Having a radical.
That having a radical. So because if it's an even radical, right, you can't take, for instance, the square root of what type of numbers? Negative numbers. So this would be x such that, so the way that we say non-negatives is x is greater than or equal to 0. You can take the square root of 0, right? The square root just means what times what equals that number. So 0 times 0 is 0, so the square root of 0 is 0. And then the last one is going to be a combination. So if you have the radical in the denominator, it's these two combined. So if x has to be greater than 0, but also can't be equal to 0, we would just say x is what? Yep, greater than 0. So we just take away the equal sign, okay? And this does work with any even root, not the odd root, because you can multiply negative numbers to get an odd. Okay, so I just asked if these domains make sense for each expression based on past algebraic properties that we've studied. Yes. Okay, and again, it's because you can't take the even root. Can't take an even root of a negative. Okay, and that's just based on the properties that when you multiply negatives together, you will end up with a positive, so we can't have that. All right, so in example 1, we're going to find the domains of the following expressions. And the first expression is going to be the square root of x plus 5 over x minus 2. Okay, so you always want to look and see, okay, do we have a radical? Do we have a fraction? And in some cases, we get both. 2 for the price of 1. So we have to make sure that we include both of those in our domain. So if it's a fraction, if you have a fraction, you know that the denominator can't be 0. So you have to set the denominator equal to 0 and solve. Okay, so to find where the limitation is, we're going to take the denominator, x minus 2, set it equal to 0. Obviously, we would add 2 to both sides, so x would not be able to be 2. Okay, and then the second part is going to be the radical. Whenever you have the even radical, you can take the radicand. Remember, the radicand's the value underneath, and set it greater than or equal to 0. And again, we're going to solve for x. Okay, and then it'll be greater than or equal because it is in the numerator, not in the denominator. All right, so if we do that, we have x plus 5 is greater than or equal to 0. Subtract 5 from both sides. And then we're going to put those together in 2 different ones. Oh, great. Yep. And then okay, so in set builder notation, you are just going to list these out. You're going to have to be able to do both, the domain in set builder and in interval. So in set builder, it's just x such that x cannot be 2 and x has to be greater than or equal to negative 5. And you can, in this case, you can write and. You can also just put like a comma in between. Okay, both of these have to happen. Right? And then some of you are going to be really good at doing the interval notation without a visual representation. I like to show you visually so you can see how we're creating the interval. So if you are thinking of this on a number line, it says x is greater than negative 5. So you have negative 5, negative 4, negative 3. Negative 2, negative 1, 0. This 1, 2. Okay, and then if you have x cannot be 2, what you want to do is put an open circle there. Okay, so we know x cannot be 2. And then with x is greater than or equal to negative 5, because it's equal to, it would be a closed circle. And then it's going all the way to the right. But because it's going through that 2, you have to keep that an open circle there. Okay, so that breaks the line up into 2 different intervals. If you have a closed circle, do you remember what kind of bracket that is? Nope, if it's open. Yep, so this would be a hard bracket here to the soft bracket. We connect it to a union. Okay, so it would go from negative 5 to 2. So the soft bracket means you don't include it. Okay, so that would be 2 is not included, and then you would start at 2, and then where is this line going? Infinity. So this would be 2 to infinity. Okay, so we have -5, comma, it's going to 2. Okay, again, some of you are going to be able to jump from here to here, but I want you to see visually what is happening in this case. All right, questions for me in part A? Yep. Okay, and then for all of these, what you're going to be asking is, do you have a fraction or do you have a radical? Okay, so for B, you have -5 x squared minus 6x minus 6. Going to give you C as well. Okay, so you're going to just ask yourself, is there a fraction? No. Is there an even root? No. So if that doesn't happen, what is your domain? All real numbers. So again, going to do it in set builder, x such that x is an element in the set of real numbers. And then an interval notation would just be -infinity to infinity. And that would be your final answer. Okay, and then for C, you can see we have a fraction. There's no radical. So if we have a fraction, what can't happen? Yeah, the denominator can't equal 0. So let's set the denominator equal to 0 and solve. So if you're going to solve this, what method are we going to use? Yep, we're going to factor. Okay, do you have to worry about factoring the numerator in this case? No, because you're only doing the domain. If it asks you to simplify, then yes, you would do that. So I'm looking for something that multiplies to 16, adds to -8, -4, and -4. When they're double like that, you know that each one is going to produce the same thing. Do you guys remember what that would be called if you were doing your solutions? Nope. But that is the one that we did last year. But if it happens more than once, multiplicity, yep. It's a good try though. Okay, so x can't be 4, so we would just say x such that x cannot be 4 in set builder. Okay, and then do you guys think that you can do that without me explaining it in interval? So again, I like to think of my number line, right? It can be anything except for 4. So it can be anything to the right and anything to the left. Whenever you're doing an interval notation, you want to start with the lowest value. Okay, in this case, the lowest value would be -infinity. And it would go up to 4, but because it doesn't include it, we have a soft bracket, and then we do a union, and you have to use the 4. You can't just go jump to the whole numbers because that misses all the decimals in between. Okay, so if it just excludes one number, you'll have a union, -infinity to 4, union 4 to infinity. All right, let's try D. Okay, so we have x over the square root of 2x plus 3. So this is the one where you have the radical in the denominator. Okay, so if you have the radical in the denominator, you take the radicand, which is just the value that's underneath. So we're going to take 2x plus 3 and put it greater than 0. Okay, so you got to do the greater than, not the greater than equal to. You'll have the equal to if the radical is in the numerator. Okay, now the rules are pretty much the same when you're solving The only thing you really have to watch out for is if you're dividing by a negative with an inequality, because then what happens? Yeah, the sign flips. Okay, so then for your domain, you have x such that x is greater than negative 3 over 2. And again, I do think visuals are helpful. So if x is greater than, it's an open circle. And then it's just everything, if it's greater than, it's going to the right. So you would start at negative 3 over 2, has to be a soft bracket because of the open circle, and then it's going to go to infinity. That would be your final answer. Mm-hmm. Mm-hmm. Yeah, the only time that wouldn't is if you have like a negative inside here, so that's divide with the flip sign. So that's going to be greater. Okay, and then here we have two things, right? We have the denominator can't be 0, but we have a radical up top where the radicand has to be greater than or equal to 0. So we have to do two separate, one equation, one inequality. Okay, so we have to find what we have to exclude based on the denominator. Okay, so you add 7, divide by 5. Is it okay if I just jump to what x can't be? Okay, so x cannot be 7/5. Right, so you add the 7, divide. Okay, and then we also have to keep in mind here the radicand, because it's on the top, it's greater than or equal to 0. The last one was just greater than because it was in the denominator. So here, 6x is greater than or equal to 0. We would just divide by 6. So if you were solving with the root, you really just square both sides, and you'd end up with this is equal to 0. So you can just take whatever's underneath. You don't even have to worry about that part. It's whatever you're taking the square root of, that's what can't be negative. So it's based on that definition as well. Okay, so I'm going to put 0 here. 7/5 I know is greater than 1, right? Okay, so this is just to help us with the visual. So if you have x is greater than or equal to 0, you would start here and go all the way to the right, but this is going to be an open circle. So when you're going all the way to the right, okay, see if you can write that in interval notation. And then for okay, so we have set builder, and then can you guys see if you can do that in interval notation? How confident are we feeling with the interval notation? Yeah, for the when you're doing the set builder, it doesn't matter to me whether you say which one of these you say first, especially in a case like this. Like sometimes I would probably say this first just because that comes second on the number line. So either way is fine. And then with interval notation, you do have to put it in this order. So you always start with the lowest value and then you go to the highest value. Okay, so the lowest value you could possibly have is 0. Is that hard bracket or soft? Hard, because it's closed. Okay, and then you keep moving along the line until you get to 7/5. and then it's open, so soft bracket, union, 7/5 to infinity and beyond. Okay. All right, and then the next thing we're going to do today is we are going to rationalize either the denominator or the numerator. And we're going to do some review on conjugates. So if a fraction has a denominator and it has this form, so it's going to be with all variables, a plus b root c, then we can rationalize the denominator, or we can use the same process for the numerator, by multiplying both of them by the conjugate radical. So the conjugate is the same value, except it would be a minus b root c. Okay, and this works because of the special product formula. Okay, if you multiply those together, then the conjugate product is not going to form a radical. So I know that's a lot of fancy words. Let's write it out and see what it means. Okay, so this is the special product. Okay, so if you were to multiply, if you were to FOIL this out, you'd have a times a, which is a squared. And then what would happen to the middle terms? They cancel out. So a times b root c is ab root c. You'd have a positive ab root c. A times negative b root c is negative ab root c, so that would make 0. And then when you multiply these two together, what's b times negative b? Negative b squared. What's root c times root c? C. So there's no more radical in there, which is why we would rationalize the denominator in the first place. Okay, so if I'm going to give you a couple of examples here. I want you to write the conjugates. So for 2 minus root 3, I want you to write the conjugate. 5 plus 2 root 5. I'm going to squeeze a third one in here. Okay, so I just want you to write the conjugates underneath those for each one. All right, so if you have 2 minus root 3, what would you multiply that by? 2 plus root 3. All right, and then if you have 5 plus 2 root 5, you multiply by 5 minus 2 root 5. Okay, and then this one always trips people up because you have 2 negatives. The only part of the conjugate that you change is what's in front of the radical. See how this is a and this is a? You don't do the opposite. So you have to keep this negative 2 and then it's plus root 7. Okay, because we didn't make this 2 negative 2, right? So we're not going to change this from a negative to a positive. Okay. All right, let's multiply. So these are different types that you did last year. Okay, and example 2 says to rationalize the denominator. Okay, so we have 12 over 1 minus root 7. So what we have to show is that we're multiplying by 1 plus root 7. So when we're doing this, we're really using FOIL on the bottom. I like to do the bottom first. That's the whole reason for this one. If it's the denominator, to make sure they cancel out. So 1 times 1 is 1. You don't have to right down the middle, but you should be checking that in your head. It's the negative root 7 and positive root 7. What's root 7 times root 7? 7. So it's 1 minus 7, just going to give us negative 6 in the denominator. Okay, and then we are always going to be simplifying these as well. When you have just one number, you distribute. So 12 times 1 is 12. 12 times root 7 is 12 root 7. So what you have to do is divide both of these by negative 6. Okay, so you want to write these as two terms. So 12 divided by negative 6 is negative 2. And this would be negative 2 root 7. This is going to be your final answer. Okay, so you always have to simplify. All right, and then for this one, the conjugate is going to be root 5 plus root x. So we're going to do that on the top and the bottom. Okay, so I'll give you a minute to boil the bottom. First outer inner lap, the first inner outer lap. All right, so what do we get in the denominator? Yeah, great. Okay, so root 5 times root 5 is 5. Negative root x times positive root x is negative x. And then, do you guys know what you would get when you multiply those together? Square root of 5x. Okay, because they're both under the square root, so you could do that. Okay? And then on top, you'd have x root 5 plus x root x. Okay, and you could leave it like this for this case specifically. Did any of you factor out the negative? Because you could do that too. So if you factored out the negative on the bottom, you'd have this. Okay, and then because this one you have the 5 minus x, you can't just cancel these out and you can't cancel these out. You can only divide if you have one term on the bottom. Okay, and then like I said, you could leave it as either one of those. Okay, so now example 3 says to rationalize the numerator. And that feels weird because you've been told all your life that you are rationalizing the denominator. So when we get into the more calc-based stuff, rationalizing the numerator applies to calculus and finding limits. So if you know anybody in calc and you hear them talking about limits, rationalizing the numerator is one way to simplify with algebra. And that's actually something that we're going to see again at the end of the year when we start getting into that stuff. So when you're rationalizing the numerator, it is very similar to the denominator. It's just now we're taking the conjugate of the top. So the conjugate of the square root of 1 plus h minus 1 is the square root of 1 plus h plus 1. So the radical stays the exact same. Okay, and then one little hint, because when we're doing this, something special is going to happen. Like I said, this is going to relate to other things we are doing down the road. We are not going to distribute. Okay, so I'm going to show you how to write that out. We are going to FOIL on top. So I know that that looks kind of big and scary. We're just going to do that step by step. So if we do the square root of 1 plus h times the square root of 1 plus h, we get 1 plus h. Now the middle and the outside are going to cancel out, inside and outside, and then negative 1 times 1 is negative 1. Okay, so in the next step, we are going to simplify that. What would the top be? Just h, okay? Now that is the reason why we are not going to distribute here. Because what is going to happen if you leave it as h times 1 plus h plus 1? They're going to cancel. So they can cancel because these are factors. They're being multiplied. So you can divide those out. And your final answer would be 1 over the square root of 1 plus h plus 1. Again, I know that probably feels a little strange, but there are going to be connections later on down the road. And then if they ask you to rationalize the numerator, and there's technically not a numerator because you don't have a fraction, that just means this whole thing is over 1. We're going to make it a fraction. Okay, and we're going to simplify the numerator.
Since the radical is on the bottom, wouldn't you have to bring it back to the top since you can't have radicals on the bottom?
So the directions for these are actually telling you to rationalize the numerator. So when they ask you to rationalize the numerator, you won't have any radicals in the numerator, and you can have them in the denominator. So it's kind of the opposite of what you've been doing for the last few years. Yep, and it'll just be based on that direction. Now, some of you might notice these are being multiplied. So if you have a radical times a radical, that's the same thing as x plus h times x. So we're just going to write that out. If I do x times x, I get x squared. And then h times x is just hx. And then you have one term added to one term here in the simplified form. Okay, so now we're going to multiply by the conjugate, which is going to be x squared plus hx minus x minus 1 in the square root. All right, so if I multiply these two together, first times first, these are the first ones I'm multiplying, I just get x squared plus hx. And then this one's a little trickier. So the inside and the outside, yep, those are going to cancel. The last ones, though, you have a binomial. What'd I do?
The one they're writing in the it's x plus 1.
Oh. No. Oh, thank you. Yes, plus. Thank you. Yeah, so it'll be, it'll just be the minus here. Once I saw multiple hands go up, I was like, oh no, what did I do? Thank you. Okay, and then when you have a binomial here, which you do, you have the x plus 1 and the x plus 1. So when you multiply that by itself, remember that you're going to have to distribute it. Okay, and then the denominator is going to stay the same. Okay, so then I'm going to distribute the negative to the x and to the 1. Okay, and in this case, nothing will cancel out, so your final answer is x squared plus hx minus x minus 1 all over the square root of x squared plus hx minus x plus 1. Okay, so it's okay to have answers that look like that. I know that's not something that we're used to. Okay, we're going to get into more complicated examples now. All right, so based on what we did for B, do you guys think you can do C without me?
Yeah.
And then when you are done with that, you can check your work with mine. You do have a cancellation there. Okay, so when you multiply, again, what's underneath the radical stays the same. The only thing that changes is that middle sign. Okay, so really when you're doing this, it is the difference of two squares. You square this to get what's underneath. The inside and the outside cancel, and then you end up squaring these, and it's going to be the opposite. Y minus y cancels. Don't forget the negative there. You have to keep the -6.